Hello everyone. My name is Juan Manuel Rodriguez Arita, a PhD student at Mechanical Laboratory of Normandy in Rouen, France. So now I'm going to present to you this topic about a stochastic method for determination of a phase change boundary. First, we're going to speak a little introduction about a stochastic method and phase change boundary. In this case, merging a solidification process. After that, we're going to show how we can find and approximate solutions with stochastic method. This is the recent work. So we can show also a comparison with finite element method with a simple example, and we can see what happened with the properties in this case. The stochastic process that we use in this work is the Brownian motion. The Brownian motion was considered by Robert Brown in 1827. He saw the erratic behavior of small particles suspended in a fluid. So later, Albert Einstein in 1905 was the first person to introduce the first probabilistic model just to explain some physical phenomena, diffusion problem, normally. So after that, the person that introduced the strong mathematical model was Nobel winner in 1927. So the stochastic method process is a perturbation. In perturbation, we can consider in our deterministic world. So what happened this perturbation in some physical phenomena? In this case, we have melting process. For example, here we have liquid phase and here solid phase. We can see how the phase change boundary is moving until the liquid phase is complete. So what happened in this case is a partial differential equation deterministic. We can solve this with a heat equation, but the principal interest is the resolution with a stochastic method. How we can do that? First, we need to consider the partial differential equation for describe the physical phenomenon. Also, we can introduce the random variable, in this case, the stochastic process or method that affect this deterministic function. So we can transform this partial differential equation, take account the stochastic method in a stochastic differential equation. We can transform this and solve this stochastic differential equation with the Heta calculus. Now we can establish the relation between the parabolic partial differential equation, for example, the heat equation, with the Heta calculus. We can do this relation with the Feyman-Kac formula. So we can find the solution of this heat equation. And finally, we can do the numerical simulation. We can do the numerical simulation with the stochastic process. So for the phase change boundary, we have here the Stefan problem. The Stefan problem in bidimensional domain, we have here the omega L, the liquid phase, and here the omega S, the solid phase, that it is divided by the phase transition or the curve of the boundary change that it is moving for any time. So here we need to introduce the Fourier law to solving this problem. So we can also introduce the heat equation for each domain, for each region, for the liquid phase and solid phase. And a very important condition to solve this problem, the Stefan problem, is necessary to work with the Stefan condition. Here we have lambda. Lambda is the diffusivity thermal capacity. Here we have the velocity of the phase transition. So it's necessary to explain that in this classical model, the material is pure and isotropic, the convection and radiation effects are neglected, and the thermal diffusivity here are here, this is the thermal capacity, are constant. Also the density here are constant. For the moment is okay, but in our case we work with this parameter can change by the temperature. But in the first case, in this classical model, these properties are constant. So for solving this Stefan problem, it's necessary to consider this heat equation for the solid and liquid phase. Here the Stefan condition, and here we have the Dirichlet condition. So we can transfer this problem of here in the heat equation in the total equation for the world domain. For solving the Stefan problem, it's necessary to consider any transformation. The first is the characteristic function with the normal velocity here of the phase transition. We need to introduce this parameter xi, that this xi is equal to 0 in solid phase and 1 in liquid phase. So we can transfer the general equation in this that depend on the parameter density, thermal capacity, also the thermal conductivity, and here the diffusivity thermal. All these parameters depend on the temperature. So in this equation, this heat equation need to satisfy the Stefan condition here. So after that, it's necessary to this transfer to the regularized equation, because we have a lot of discontinuity in here in the phase change boundary. So with the regularized equation we can solve this problem. Now we're going to consider the stochastic approach. First, we have the heat equation for a Stefan problem. Here we have the derivative of this process xt that depend of the Brownian or Wiener process. So after that, we introduce the ether calculus to solving this equation, this partial differential equation with this stochastic process. So we can find this stochastic equation dyt. So finally we can apply Feyman-Kac formula, and we have an approximation solution of the Stefan problem. Here we have U is theta is the temperature, is equal to y0, and y0 is equal to the expectation of yt. Here U depends of the space and time, because the phase transition change for all t, And in practice, we generate a sample of y1, y1, y2, y3, y number of sample. So from here, from the yt, and we approximate this expectation by the empirical mean of the sample. This is how we can get the solution. And second method for the determination of the Stefan boundary here is with the domain optimization. In this case, we use a signal function or this alternative form. So maybe solve this equation by adapted methods. One of them is the minimization of the difference between the left here and the right side of the equality. So this is a case of the optimization. And finally, in this case, we're going to consider the third method for determination of the Stefan boundary. In this case, we're going to consider the discretization in time for the partial difference equation. So after applying the stochastic process, we can discretize the partial differential equation and solve this with the stochastic method, Ito formula, also Feyman-Kac formula, and we solve this equation. So it's the same that the first method. So we need only generate number of sample of the expectation of yt, if remembering the last slide, after approximate the solution for all t. Now we're going to speak briefly about the finite element approach. Here we need to consider the shape function for different number of elements. We can transform the principal heat equation in this two form. Here M is the mass matrix associated to the density, and here F is the force matrix associated at this equation. If you remember, we had introduced the parameter Xi for the Stefan boundary, so we need to solve the system of differential equation, and this equation must be discretized. So for that, here we show the different discretization that we had used for this topic. The first third line corresponds to this equation, the equation 25, and the other three correspond to the equation 26. So we use 6 different discretization to solve the problem with the finite element approach. Now we consider a simple example for find an approximate solution of the Stefan problem. In this case, they are the properties, and we have the function that we know. Remember that now we assume that we know the boundary Stefan position at time t0. This is deterministic, and here we know the Stefan condition at time t1. So in the result we have here the red point is the approximative solution with stochastic method, and here we can see the convergence of the method is work very good. Now we have, with the same numerical example, we present this table with finite element result. In first instance, we have here the stochastic method. This method is meshless, so we have also other 12 finite element approach. The first is corresponding to T2. T2 is triangle element with 4 nodes, and the other 6 finite element approach corresponding to quadrangle elements with 9 nodes. For the number 1, 2, 3, 4, 5, and 6 is this the mean corresponding to the different discretization that we had saw before for finite element. So here we can see the stochastic method had good approximation in comparison with the triangle method, with the triangle element, and the quadrangle method had better approximation to the solution. We can see that here, and here we show a bidimensional Stefan problem in finite element method. Here we have the blue region is the liquid region, and red region is the solid region. We have here the the phase change boundary, or the Stefan condition, how this boundary is moving until time t equal 1. And here we have the same model but in 3D. And finally, we consider the experimental data of the physical properties for a Stefan problem. This property depends on the temperature. In this case, the critical temperature is 247. This temperature find this. So, since the table does not contain enough data, we interpolate the data using an artificial neural network. So, we train it with data completely by the collocation approach of uncertainty quantification. Here we can see in this blue area is the liquid region, and here red is the solid region, we can see the variability of the domains for t equal to 1 and for different critical temperatures. The regions appear as regular due to the property of the different partial equations that we consider. So, in conclusion, we saw how the stochastic method is a method very flexible because this method don't have mesh, so it's more easy for parallelize, and this method had a good approximation in comparison with the finite element method triangle and quadrangle. We had saw also that the quadrangle had better approximation than triangle and stochastic method, but the stochastic method is a method very flexible that quickly we can show we can find an approximative solution for the Stefan problem or phase change boundary. So this is a good advantage in comparison with the finite element method. So this method has disadvantage the mesh, of course, respect with the stochastic method, and also it's more difficult to parallelize. In future work, we will consider other discretization methods and work on a sphere approach for test the stochastic method to find a better approximation, and also the consideration of the uncertainty quantification for manipulation of the probability space, because the regions are probability space. It does mean that in b-dimensional this region or surface and in the space R3 they are volume. So thanks for your attention. If you have any question, please contact me by email. This is all. Thank you.